Hello, everyone. We're pleased to meet you all today. My name is Etienne Almoric. I'm the CEO of Febus Optics, and today I'm with my colleague Pierre Clément, who is a technical lead in power cable monitoring. We present you our company first, and especially what's the technology behind it, distributed fiber sensing. And then we come to our offer in power cable monitoring to go in detail in what we propose to the market today, what we offer. So, as a company, we are a French company, manufacturer of distributed fiber sensing, in particular DTS, DSS, and DAS. I'll come back to that and explain exactly what that means. Today, we operate in more than 25 countries. We have a worldwide activity. And we put a lot of effort in both production, where we standardized. We invest a lot in our production to have a standardized capacity, and also in R&D, in order to continuously improve our equipment, but also launch some new innovation. To the market, we are capable to offer a wide range of products and services, from preliminary studies to a complete install solutions, which we will come to it because that's what we do for power cable. Complete install solution with long-term maintenance. Today we're based in Pau, southwest of France, where we have our production capability, R&D, and also a large test center. We're also based in Paris and Strasbourg, and we have commercial representation now in Houston, in North Africa, and in Abu Dhabi, in the Middle East. So, I wanted to take a minute to describe our unique test center. It gives us a lot of possibility. With it, we can accelerate the development of a technology, but also conduct on-custom tests and specific tests to demonstrate our technology. So you're all welcome to contact us to have a demonstration of our technology and see how distributed fiber sensing can work for your specific application. For power cable, more specifically, we conduct tests on thermal behavior of power cable for both grid but also underwater cable, and mechanical study out of it, where we can put some tensile load or also bending curvature on the cable and show how we detect and monitor that. So this test center, we use it also for training. We give some training on how distributed sensing works and the theory behind it. So what is the technology? How does distributed fiber sensing works? I'll take a minute to explain what it is. What we produce is a box you see on the top left. It's a concentrated technology of optics, electronics, and high-performance computing. And we can plug it into an existing fiber. Any existing fiber, actually. That's one of the big advantages of this technology, is we can use it on, for example, an existing cable that you already have, and you want to install some surveillance or integrity monitoring out of it. We can do that. The technology will launch a laser pulse in the fiber, and in some way will scan it. What will really happen is that the laser pulse will propagate over tens and tens of kilometers and generate a little bit of backscattering. This backscattering part of the energy comes back to the equipment, and we are capable of extracting from that three main parameters: strain, temperature, and acoustic vibration. So out of these three parameters, that will explain all the application we can address. And because we know exactly the speed of light, the speed of this laser pulse in the fiber, we know exactly from where this backscattering is coming from, so that we can transform a 100-kilometer long fiber into 100,000 sensors of either temperature, strain, or acoustic vibration. And this we can do it in real time and add some automatic alerting system on it. So with that, we can address a large range of applications. In seismology, we do seismology, but also active seismic. We do perimeter security and defense, where we detect anyone that comes nearby a fence, where the fiber is either buried or on the fence. We do pipeline monitoring, where we detect leak. We detect landslide, or we can detect also third-party intrusion. We do well monitoring for oil and gas, but for geothermics also, and even for some mining application, where we combine our different technology, temperature, strain, or acoustic. And also infrastructure monitoring, what we call structural health monitoring, where the fiber can be either buried in the ground or embedded into a concrete structure. It can be a bridge, a tunnel, a dike, or a nuclear power plant. And finally, the most important today, and the main focus of Febus Optics, is a power cable. where we really brings a lot of added value because we manufacture the full spectrum of distributed sensing today, and we combine them into a complete offering for the power cable monitoring. And my colleague will really detail and explain how that works. So I will now leave the floor to Pierre Clément, who will explain you in detail what is our offering in power cable monitoring. Thank you.
So thank you, Etienne, for this introduction. So as said, I will explain you in detail what we can do with distributed fiber sensing. So with distributed fiber sensing, we can have a complete power cable monitoring using both DTS and DAS, so temperature sensing, but also acoustic sensing. With temperature sensing, we have possibility to detect cable hotspots, detect, but also localize all along the fiber, so all along the cable. We can also use Rttr software for real-time thermal rating to enhance the production through the cable. And with a DAS system, we can detect and localize faults, shocks, cable movements, partial discharges. All these measurements can be merged in a standalone alerting software or also integrated directly to your SCADA. Through our R&D activities, we've also shown the ability of distributed fiber sensing to detect and measure the fatigue of the dynamic cables, also detect the marine mammals, and boat tracking. So now let's go in detail with the DTS applications for power cable. So as I said, we can measure hotspot. So hotspot is an elevation of the core conductor temperature, but also an elevation of the fiber which is inside the power cable. So as you can see on the graph, let's show you here. As you can see on the graph here, on the y-axis you have the temperature measurement from our DTS, in the x is the distance. We see an increase of the temperature, which is very localized, and we can know its position. This increase of temperature, if we define a threshold, and if the temperature goes beyond this threshold, we can generate alerts and give this exact GPS position. Another thing is Rttr Algorithm, which is a software that uses the temperature of the fiber inside the cable and couples this temperature to the numerical thermal models, the cables, but also the environment where the cable is, and also the current that goes through the cable. The numerical simulation gives then, over time, but also forecast the conductor temperature value. This can give an information to the electrical suppliers that can adapt the current load to prevent any failures. So this Rttr software is fully integrated to the solution, to the alerting solution of Febus. Now let's switch to the DAS application for the acoustic. So with DAS, we can detect shocks, faults, and localize it. For example, a shock, an onshore that is having an impact on the cables, create a vibration on the fiber that we detect. Here you see the red curve here is the measurement noise from the DAS when nothing is happening on the cable. On the blue curves is when an onshore is hitting the cable. And you see this impulsive signal, which is characteristic to an impact and is measurable by the DAS system. We are also able to detect cable movements for the static cable. For example, the slow movements due to suspension zones create an oscillation which is low frequency and can decrease the cable lifetime due to the fatigue. So with that system, by plugging the equipment directly on the fiber and making a fast measurement, we can quickly see the suspension zone all along the cable. For example, we have here an example of a measurement on an offshore cable. It's a telecommunication cable. This measurement has been published in Nature. And the aim of this measurement was not to detect free spans, it was to detect earthquakes. But during this measurement, we've seen 3 parts of the cable with a high amplitude of acoustic vibrations caused by these free spans. What you can see here on the black, red, and blue curves, you see the oscillation, which are very low frequency, around 0.5 Hertz, and due to this slow motion of the cable due to the free span. We've correlated the position that we detected with DAS to the position that corresponding to the lack of slack seen during the installation. Another thing is a measurement we did on a subsea cable in the Atlantic Ocean, and this is the same time. Here you see the measurement directly from the DAS system. On the y-axis you have the time, on the x you have the distance, and you see this part moving, which is caused by a suspension zone. You have a slice here of the graph, and the blue curve is a buried part of the cable where nothing is happening. The red curve is a suspended zone when you see this oscillation of the cable. So another thing is to measure the dynamic part of the cable using DAS system. We are actually performing measurements on the EMEC-Orkney test site using DAS on their dynamic parts of the cables. This monitoring lasts over 1 month to have a complete tidal cycle. And with this, we can correlate DAS with the fatigue of the cable. Another event detected by DAS is partial discharges. DAS systems is able to replace standard partial discharges sensors because of the vibrating signal created by partial discharges at 50 Hz, 100 Hz, and also the harmonic contributions. Here you see that we've performed a measurement on a cable with the partial discharges. You see where positions where there is no discharges, you get a signal, a contribution signal at 100 Hz, which is close to the noise level. But the power spectral density is increasing at the position where you have the partial discharges. So in addition to standard PD sensors, the DAS can localize and detect all over the cable these events. For example, for Nexans, we performed measurement on a cable, on a 4 kilometers cable, where partial discharges were present all along the cable. And we performed DAS measurement, but also PD sensors, conventional methods, to detect these events. An external generator, an AC voltage, was generating a current with voltage increasing up to 8.5 kilovolts and at 50 Hertz. Oh, sorry. The results have shown that the power spectral density at 100 Hz is increasing accordingly the voltage, and the power spectrum is also increasing. Here you have the contribution at 100 Hz increasing with the voltage. This measurement, this contribution is disappearing when the voltage is turned off, and this is repeatable with the applied voltage. So, to address all these type of events, to address this complete monitoring of cable, we need all the products that we manufacture with the largest distributed fiber optic sensing offer. The G series for temperature and strain, A series for acoustic, and T series only for temperature. The length of measurement is about 70, 80 kilometers, but this is something that can be enhanced with some in-house repeater, and we can go to 200 kilometers. These interrogation units are integrated to the complete solution using softwares for the acquisition, but also data processing, like the Rttr, but also with that system event recognition, and go to the forward software that generates the alert and communicate also the alert to the SCADA, for example. The forward client for the visualization can give you a mapping of the cable and give you the GPS position at every position of the fiber. So that's it for the presentation of what we can do. We have a booth on the day 16, so you're welcome to come to visit us. We will show you some DTS measurement. We have a hotspot demonstration and also a forward software demonstration. So thank you, and this is the result of what we can do with distributed fiber sensing.